That's a picture of the best piston engine in general aviation today. It's a Continental IO550. Best means lots of power, smooth running, and economical. If anything, burning 16 gallons an hour can be thought of as economical. In this airplane, that's a Cirrus SR-22T, that's 190 knots at 12 miles per gallon. Ain't no Prius, but it goes 3 times as fast. This is a picture of the most sophisticated piston engine in general aviation today, the Austro A330. It powers this, the Diamond DA62 twin, which, according to me, is the most refined and well sorted out airplane in general aviation today. If you've got 1.2 million, Diamond will build you one. I'd like mine in this metallic red, please. In a previous video on engine failures, lots of viewers suggested that car engines don't work in airplanes or aren't reliable because they can't run at 70% power continuously. Fair point, and a common belief, but also a myth. Back to the AE330. This is a car engine, a diesel car engine. With a few modifications, it's straight off the Mercedes-Benz assembly line. It runs at 70% power all day for 1,800 hours. Has a full-up FADEC, electronic fuel injection, and onboard diagnostic capability. So if so great, why aren't there more of them flying? If I toss up one of my annoying oh hell, I'm sick of pie. Let's use a cake chart. Continental and Lycoming are represented by the 2 thick layers. Rotax has the thin layer of frosting in the middle, and Austro is the barely there frosting on the top. So what gives here? It's a long and bumpy story, mostly shaped by industrial and market inertia, customers who say they want new sophisticated stuff but really aren't that adventurous, and by new engine ideas that were underfunded or just didn't work that well to begin with, but mostly by this undeniable fact. It's fun to bash these old aircraft engines as dinosaurs invented in the 1960s, but, well, they actually work. For all their foibles, everyone knows what they cost, how they perform, and how reliable they're likely to be. So when it's time to write a check for a new engine, not too many buyers snag their pants on the lack of dual overhead cams or OBD. While general aviation isn't exactly cheek by jowl with cutting-edge engines, it's not entirely for lack of trying. Let's start with this engine, which, if you are a connoisseur of aviation projects that turned into craters, you will recognize as the Rotax V6, whose marketing name eventually became Rev. 2 versions were planned, one at 225 horsepower and one at 300. It was announced with great secretive fanfare in 2003, and by 2006, it was just another rusting hulk in the graveyard of aviation dead-enders. Rotax killed it. Probably rightly. This engine should have satisfied the supposed appetite for automotive-type high technology. It was a V6 with overhead cams, fuel injection, and electronic ignition. All the stuff you'd expect in a modern engine. Cirrus actually wanted it and had test flown it to replace the Continental IO360 in the SR20, which was a little underpowered. Rotax had even invested in a V6 production equipment line at its Austrian factory, and it was ready to rock. So why don't we have V6 powered SR20s? Good question. From what we can tell, the answer is that the engine needed more work. The basic structural geometry wasn't quite right. More investment was needed. At the time, Rotax's Canadian mothership, that was Bombardier, had sold off the Austrian engine factory, and the interest just wasn't there to carry on with the V6. There were probably inside corporate intrigues that we don't know about too. But if they had gone forward with it, would it have succeeded? Maybe, maybe not. An engine project this ambitious needs field technical support and overhaul facilities, and above all, warranty support. At the time, Rotax already had a reputation in the US for not being good at that stuff, and mechanics complained about the 900 series engines being difficult to service. But they really weren't. They were just different. What unfolded the following year in 2007 would have shown Rotax the sort of bullet it dodged when it abandoned the V6. At the Berlin Air Show in 2002, when Diamond Aircraft introduced this, the DA-42, it violated an unwritten rule in airplane design, which is it's risky to introduce an untried engine in an untried airframe. To be fair, the airframe was based on this, the DA-40 single, yet it was still a departure. But the engine was something else. It was the Thielert 1.7 Centurion, an adaptation of the Mercedes-Benz OM640 diesel MB used in these cars, the A-Class sedans. These were sold in the bazillions, with the engine being the beneficiary of millions of euros of development. It had all the latest technology: dual overhead camshafts, 4 valves per cylinder, turbocharging and common rail fuel injection, and electronic controls. It was about as bulletproof as engines get. Thielert played quite the contorted word game, distancing itself from Mercedes-Benz, insisting that the Centurion wasn't a car engine and that half the parts in the Centurion were built by Thielert, some to lighten it for aircraft use. But then the trouble started. The airplane itself was well received, especially by flight schools who needed twins for the airline market training. The DA-42 was a delight to fly, and although it never achieved the aspirational 200 knots, the engines were smooth and easy to operate. But by 2007, owners were complaining about AOG maintenance issues. A lot of owners. There were problems with cylinder heads cracking, piston lubrication, pump failures, and at least 22 engine stoppages. The gearbox was a major headache. It was supposed to be removed and inspected every 300 hours, and owners said Thielert vastly underestimated the labor hours necessary to do that work. Thielert promised a rapid increase in gearbox intervals, but it was years in coming. By then, Thielert was bankrupt. There was little fundamentally wrong with the engine. Its problems were just teething pains. The business failed because Thielert overpromised on performance and botched warranty response and economics. This fiasco very nearly took Diamond down with it, since angry owners expected Diamond to fix engines that Thielert couldn't or wouldn't. The situation so pissed off this man, Diamond Aircraft founder Christian Dries, that he started his own engine company, and that's Austro. When I visited the Austro factory to shoot this video, Dries pointed to a spanking new Mercedes-Benz OM640 on the factory floor. Yep, the very same one Thielert used as the basis for its engine, and he said, "You cannot improve on this." And Austro didn't try. They took the engine straight off the Benz assembly line, stripped off certain automotive components, installed the gearbox and other aviation components, and had themselves an engine. Recently, Austro has been manufacturing the core engine themselves. There's one good reason why the Austro engine should not have succeeded, and one good reason why it did. Austro retained the original Mercedes-Benz cast iron block, which means the engine weighs 112 pounds more than the Thielert version did. That could be a deal killer, especially in a twin where the weight gain is ×2. A typical airframer would understandably look for a lighter engine. But Christian Dries was providing engines for his own airframes and decided to invest the money to certify both the single and the twin to a higher weight to accommodate the heavier engine. Before the company failed, Thielert also tried to market this behemoth, the Centurion 4.0. It's also a Mercedes diesel, a turbocharged 32-valve V8 used in the S-Class Benz. These are the ones that blow by you at $1.50 on the Autobahn while the driver puffs on camels. At 628 pounds, it's 200 pounds heavier than the Continental IO 550 for similar horsepower. Again, Sears considered it for the SR22, but like Diamond, it would have had to re-engineer the airplane for the higher weight. Doable, yes, but for what gain? Evidently not much. Let's look at some numbers to see how that big V8 would have compared to the Continental IO 550. Its higher weight means a lower power to weight ratio, about 40% lower. What it loses in power to weight, it gains in fuel efficiency. The diesel can run at a brake-specific fuel consumption of about 0.34 to 0.35, but the IO 550 is no slouch either. It will operate all day at 0.38 to 0.39 running lean and peak. At 70% power for both of them, that's a difference between 11.8 and 14 gallons per hour. So for the equivalent weight of fuel, the diesel enjoys a range advantage. This has proven out in the real world. These graphics show how the Austro diesel in Diamond's DA40NG provides a slight range advantage over the Lycoming version of the same airplane. In the US, Jet A for the diesel is about 50 cents cheaper than 100 low lead for the IO 550, so that works out to an $18 an hour advantage. It's a bigger advantage in Europe, where avgas is north of 10 bucks a gallon. That ain't chicken feed for sure, but it's never been clear to me that a buyer who can afford a nearly $1 million airplane cares that much about fuel prices, although some flight schools seem to. What was really expected to launch diesel aircraft engines to dominance was the disappearance of 100 low-lead avgas. Aviation journalists, like me, have been saying this for 40 years, and the damn stuff just won't go away, although it's hard to find in some parts of the world. But Jet A, what the diesels burn, it's everywhere. Aircraft diesels have another advantage. They're easier to operate. Ever start an IO 550? Well, you prime it first, then get the mixture set, crack the throttle, not too much, crank it, fires right up, but it doesn't catch. So you got to prime it some more, not too much, set the throttle, hold your mouth just right, crank it, and it starts right up. If the engine is warm, there's a procedure to start it that works every time, but nobody knows what it is. Usually it involves starting with the throttle wide open, so it scares the hell out of everyone on the ramp. When it's really cold, you got to drag a portable furnace out to the airplane and heat it up for 15 minutes. Yes, we're still doing this. With the diesel, just push the start button. If it's really cold, turn on the glow plugs for 40 seconds. There's no mixture control in the diesels, and in the Diamonds, no prop control either. If one engine quits in the twins and you have to cage it, right, just flip the switch, it feathers itself. It's kind of amazing to think that 20 years into the 21st century, a gasoline-powered twin still has 6 levers to operate the engines. Literally, a steam locomotive gets by on 2. The single power lever idea has been the holy grail for at least 40 years, and that gets us to another engine idea that looked great on paper, the Porsche Mooney. In 1985, these two companies thought buyers would resonate with a Porsche Boxer engine stuffed into a slick Mooney airframe. Mooney even stretched the cabin to sweeten the deal. Cue the list: 6 cylinders, overhead cams, electronic ignition, tuned induction, fan cooling, automatic mixture, and prop controls. For Pete's sake, who wouldn't want a freaking Porsche engine in their airplane? Evidently, hardly anyone did, except for 41 adventurous souls who bought the airplane before Porsche bailed on it a couple of years after it was introduced. This should have been a slam dunk, but it wasn't. As with the Thielert diesel, the engine had teething pains, problems with valve springs mainly. After good support initially, Porsche promised to fix it, but never did. I don't know, this seems like a German thing. Anyway, the owners got pissed and sued, and Porsche eventually paid to have the engines replaced with, wait for it, the Continental IO 550. Some of the PFM Mooneys were shredded by Hurricane Charlie, which struck Punta Gorda, Florida in 2004. The Mooneys were there for the conversion. When Mooney was bought by Chinese interest in 2013, the company came with all the factory tooling and manufacturing rights, and also a case of amnesia. A year after the purchase, Mooney announced the 3-seat M10 trainer powered by, you guessed it, the same Thielert diesel engine Diamond swore at. Except it wasn't exactly the same. The engine had been sorted out by then and was and is still made by Continental, who snapped up Thielert out of bankruptcy in 2013. Within 3 years, Mooney canned the M10 project, but actually it might have been a nice little airplane with the improved engine. But they realized there was just no substantial market for a trainer costing north of $300,000. The engine may have been irrelevant. Not to be denied its Me Too moment in diesel world, Cessna announced in 2007 that it would offer a diesel version of the venerable Skyhawk. The airplane was already approved for the Thielert engine under an STC. But then Cessna caught wind of Thielert's troubles, and say what you might about Cessna, it has seen enough of the aeronautical river to recognize a turd floating past when it sees one. That project was quietly canceled. Undeterred, Cessna tried again with this engine in the 182. That was in 2012. It's the SR305 diesel from SMA. They bailed on that project soon afterwards. Cirrus tried this engine too and couldn't make it work. It had significant cold starting and cold weather problems. By the way, that STC, that supplemental type certificate, in case you're unfamiliar, for the improved Thielert Continental engine allowed several companies to offer diesel conversions for the Skyhawk. These have found some traction, but the volume is really small. One that vividly illustrates how the market doesn't always embrace new technology is this one. This is the Redbird Redhawk. You'll know Redbird as the simulator company, but in 2013, it started an ambitious project to refurbish older Skyhawks with the improved Thielert engine and new avionics. Here's how the numbers worked out on that, which is to say pretty favorably. Great flying airplane too. At the time the Redhawk was introduced, its operating costs were only slightly less than the gasoline version, but these improved as the engine got a higher TBR. That's time between replacement. Redbird sold about 15 of these airplanes, but here's where it gets interesting. Redbird submitted a bid to replace the fleet of a major flight university, and they won on the low bid, but they didn't get the order. And why not? Probably because the big schools aren't as interested in low operating costs as they are in predictability, reliability, and dispatchability, and they didn't want to invest in new support infrastructure for the diesel. They know what a new Skyhawk and an Archer will do, and there is still a long memory about Diamond's Thielert troubles. Also, Redbird had continuing problems getting the engines and parts delivered from Germany on time. At the time, there was no U.S. service center for the engines. Piper now offers the Continental version of the diesel in the Archer DX, and it has found some buyers, but not a lot. Okay, summing up here, Mercedes-Benz, Porsche, Thielert, Continental, is there anyone I've forgotten? Oh yeah, Toyota and Honda. In the mid-1990s, Toyota engaged a bunch of smart engineers at Hamilton Standard to certify this, a Lexus V8 for aircraft use. It became the FV4002TC, and they didn't just certify it, they got a production type certificate. They could have started building and shipping it. Cirrus would have bought it for sure, except Cirrus wasn't a thing back then. This would have been a kick-ass airplane motor. 360 horsepower, FADEC controlled and water cooled. Weighed about 520 pounds and had a best BSFC around 0.39. It's almost a high-tech IO 550. Why didn't they take over aviation with this terrific engine? I can never get an answer on why they didn't go forward, but I suspect someone in the Toyota C-suite said, "Are you people nuts? All this liability to sell 300 engines a year?" Back then, Lexus was building about 100,000 cars a year. Honda was pumping out the cars then too, and a few years later, it revealed as how it was working on something called the HAP engine in a partnership with Continental. It was a four-cylinder, water-cooled design with 225 horsepower. That's a really nice number for a light four-banger. But Honda apparently lost interest. The engine, by the way, used the same FADEC that Hamilton Standard developed for the Toyota Lexus engine. If all this gives you the impression that new engines for airplanes are a gaping black hole, well, maybe you have to be slightly delusional to propose one. And there are successes, like these three, the Rotax 912IS, the Lycoming IO390, and the new but little celebrated Lycoming IE2. The IS is almost a standard in the light sport industry now, and it's just an improved version of the 912, with fuel injection and electronic ignition. The IO390 was developed from the IO360 as an experimental engine, and is finding market traction as a replacement and finally found a spot in the Cirrus SR20. That only took about 18 years. The IE2 is based on the IO540, and it's the intriguing one here. It's a fully electronic engine used in the Tecnam P212 Traveler I reported on recently from Sun & Fun. I'll do a detailed video on it later. One thing all of these successful engines have in common is that they aren't clean sheet designs, but incremental improvements on successful engines. The IO550 is another example of that, and not an overhead cam in the bunch. Historically, new engines haven't always failed because the tech didn't work or because automotive engines can't hack the airplane duty cycle. They failed for lack of will, with will sometimes being defined as money. Think of Venn diagrams, which I like to call circles of audacity. One of the circles isn't that buyers want the thing, because buyers don't know what they want until they see it. Alan Klapmeyer of Cirrus likes to remind people that Cirrus market surveys revealed nobody wanted glass panels, but everybody bought them when they became available. To succeed, the funding, and let's just call that commitment, has to be there. It wasn't for Rotax, Toyota, or Honda. Another recent failure worth a mention is the EPS 8-cylinder diesel. Great on paper, ran out of money. To succeed, the engine has to actually do something better than what it replaces. It has to work. The Porsche engine didn't and was a little worse. The SMA diesel is another example of just not working. Finally, the whole enterprise rides on support and warranty. Without that, you get a Thielert or a Porsche and a lasting bad taste in the market. In retrospect, the Austro engine never should have succeeded. It's expensive, heavy, and complex to manufacture. Many people, including me, thought it couldn't succeed. I mean, seriously, a cast iron block in an airplane engine? Today, Diamond owns the light twin market. They sell more twins than Piper, Tecnam, and Textron combined, almost all diesel. The reason the Austro did succeed, if at low volume, is sheer force of stubborn will by Christian Dries, who forced the circles together against the laws of nature. And if you want to build a new airplane engine and succeed, that's evidently what it takes. For AdWeb, I'm Paul Bertorelli. Thanks for watching.